Well, hearty hello to you. You have reached the video on kinematics, which is the study of objects in motion. And we've reached this point in calculus where we've taken derivatives. It's gone on forever, it seems. And now we're going to actually start doing a whole lot more application things. In this case, um, anytime we talk about objects in motion, all right, we're going to talk about calculus. And really, as we go forward and we do this overview, there's a lot of introduction and a lot of definitions. But the study of calculus, all right, originated with the study of objects in motion, going back to Galileo, all right, and Newton, and the study of all these sort of objects that are moving, planetary motion, etc. And so this is like the origins of calculus right here. So we're going to do a lot of terminology and a couple of multi-part examples to get you the idea of kinematics and how calculus relates to it. So, quick introductions for our terms that we need to know. First of all, we call our position function our first thing that we have, which is sometimes symbolized by an s of t, an x of t, or a y of t, depending on the situation. So if like we're moving along the x-axis or the y-axis, we call it x or y, and just by tradition, we call position s of t. And this function will describe the location of a particle or an object at a certain point. All right, we also have this term velocity, which is defined to be the change in position over time. So it's the derivative. What would you expect? The derivative, in fact, of our position function or the slope of that position function. So formally, we say v of t is s prime of t or ds dt. All right, and the units of velocity are typically measured in units of position over units of time, such as miles per hour or feet per second. A particle is said to be stopped if our velocity is equal to 0 at a particular instant. By definition, we'll say that if v of t is bigger than 0, the particle either moves right if the particle is moving along the x-axis, or moves up if the particle moves along the y-axis. And by the way, I should make a quick little note about the word particle. We're simplifying a lot of things as we start to talk about velocity and calculus. All right, we talk about this particle, which has like kind of almost no dimension or anything to it. Right, but obviously, when we're moving in real life, we have three-dimensional objects. Right, so the particle is just kind of like our starting point to talk about velocity, etc. And typically, when we're going to talk about this early on, we're going to be talking about movement that goes in one dimension. So either right or left, or up or down. So to finish this off, if v of t is less than 0, the particle moves left or moves down, depending on the situation. Another function which will be important is what we call speed, and speed is defined as the absolute value of velocity, and it's something that's always positive. We're going to talk more about speed in the next video, but just kind of be aware that we're going to make a distinction between speed and velocity in this case. Another thing to point out basically is that velocity is speed with direction. So with velocity, you can move either to the left or to the right, east, north, south, whatever direction you want to move in. All right, and we're going to incorporate our direction in our velocity, so it could be positive or negative depending on which direction you're going in. Speed is something that's always positive, and we have this nice little speedometer right here to help us remember that, right? On a speedometer, you're never going to see negative 20 miles per hour. It doesn't make any sense. All right, and we also have this term called acceleration, which is defined as the change in velocity over change in time. All right, that'll be key to understand. Acceleration and speed are two very different concepts. Acceleration has to do with our accelerator in our car, for example, right? If you accelerate in your car, that means your velocity is increasing, assuming you're moving forward. And of course, this connects to the derivative of velocity. Acceleration is the derivative of velocity and what we call the second derivative of position. So here's our notations here. Acceleration is dv dt. It's also the second derivative of s with respect to time twice. To kind of summarize, acceleration is the first derivative of velocity, second derivative of position, and the units of acceleration are measured in distance per time, or distance per time squared. So often you'll see something like feet per second squared or miles per hour squared, right? It's the change in your velocity as time changes. That's tough to say. All right, our first example here, all right, we have a fish. Oh, look at the little fish off to the side there. He's moving along the x-axis, so its position at any time bigger than or equal to 0 is given by this function. S of t equals 4/3 t cubed minus 13t squared plus 22t minus 5, where S is measured in meters and T is measured in seconds. So first of all, let's see if we can find the instantaneous velocity at any time t. So velocity is the derivative of position, so we get 4t squared when we take the derivative of 4/3 t cubed minus 26t plus 22. Let's say we wanted to find our velocity at time 2. So the velocity is what we get when we plug 2 into this function. So we get 4 times 2 squared minus 26 times 2 plus 22, which ends up being negative 14 meters per second. All right, the fish disappeared. It was tired. But it's still moving along the x-axis, all right, in that nice position function. And we want to know when the fish is at rest. Well, the fish is at rest at time and whenever velocity is equal to 0. So we take our velocity function, which we found out before. We can factor out a 0, and we get 2 times, or factor out a 2, excuse me, and get a 2 times 2t squared minus 13t plus 11, which factors to 2 times 2t minus 11 times t minus 1. And if we set each of these factors equal to 0, we get 2 times when the fish is at rest at time 1 and at time 5.5. All right. When does the fish move backwards? When does it move forwards? All right. So again, we've got our velocity function. We already figured out that the fish is at rest at 1 and at 5.5. And for whatever reason, could stop at 10. I don't know why that's there, but basically, here's our nice little sign test. And on our test, we're going to test where the derivative is positive and where the derivative is negative. So we put these values right here where velocity is equal to 0 at 1 and at 5.5. All right, and when we do our test, we're going to test numbers a little bit to the left of 1, but bigger than 0. Right, when we plug those in, we get a positive number for velocity. Numbers between 1 and 5.5 give us a negative number, and between 5.5 and beyond, we get a positive velocity. All right, so all we're doing, by the way, I know I didn't make this clear, but we're plugging into this velocity function right here, 2 times 2t minus 11 times t minus 1, which is just a quadratic that opens up on both sides. All right, and so it's going to be positive on either side of 1 and of 5.5, and then negative in between. So this particle moves forward from 0 to 1, 5.5 to infinity, and backwards from 1 to 5.5. All right, last part of this, we got the same fish. It's still moving along the same position function. We want to find the acceleration of the fish at any time t using our appropriate units. So acceleration is the derivative of velocity. We already figured out velocity was 4t squared minus 26t plus 22. Acceleration is the derivative of our velocity, which is 8t minus 26. And since the velocity was measured in meters per second, acceleration will be meters per second, or meters per second squared. All right, last example here. Let's see if we can try to connect our graphs to our ideas of velocity and acceleration. So let's say the position of a particle is given by the equation s of t is t cubed minus 6t squared plus 9t plus 2, and all the graphs of position, velocity, and acceleration are seen below. So position is a nice cubic function that makes velocity a quadratic, and acceleration is a line, as we take the derivatives by power rule. First of all, what's the equation for the velocity of the particle? Well, take the derivative. We get 3t squared minus 12t plus 9. For what values of t is the particle at rest? How can we use our velocity graph to justify this answer? Well, in this case, the particle is at rest whenever v of t is equal to 0, which will be at 1 and at 3. For what values of t does the particle move backwards or forwards? And use this velocity graph to justify your answer. So, particle moves forward whenever velocity is positive. It will be from negative infinity to 1 and 3 to infinity. And the particle moves backwards when velocity is less than 0, which occurs from 1 to 3. Finally, for what value of t is the acceleration 0, and what does this situation where acceleration 0 mean in the context of the problem? The acceleration is 0, as we can see from our acceleration graph, when t is equal to 2. Now, we could have noticed that from our velocity graph because at time 2, the velocity stops decreasing and starts to increase. So it's a change in our velocity going from decreasing to increasing. It could have happened the other way around, but that's what happened here. And one way of looking at it, this is that it would be our maximum speed when we're moving backwards. So we're moving backwards very quickly, and then at 2 we start to move backwards, but a whole lot slower. and then up until time 3 when the particle or whatever it is stops and then starts moving forward again because the velocity is positive. How can we tell from the graph of velocity that acceleration is negative? Well, remember, velocity and accelerations are related in that acceleration is the derivative of velocity. So acceleration is negative whenever velocity decreases, right? That's from negative infinity to 2, right? So remember that relationship between a derivative and a function. So in this case, the first derivative, velocity, and the second derivative, acceleration, are related to each other because acceleration is the derivative of velocity. If we wanted to find where acceleration was positive, we would say that's from 2 to infinity because velocity is increasing there. All right, so in summary, so many terms to know. We got velocity, we got acceleration, we got speed, but calculus and derivatives tie them all together, and they can be applied to equations, graphs, and later tables when we get to those in class. When can we use this? All the time. Anytime something's moving, calculus is involved. Well, you thought, hey, when am I going to use this? And now you know, every day. Good luck.